manifold groups.
Thanks a lot. Yeah, so I just tried to copy the title of my talk from this spreadsheet, and then I realized the title is really too long, so let me just put separability of surface subgroups, because that's something that I would like to talk about mostly in three manifold groups. And just to put in group theoretic terms, that means if you're considering a surface subgroup inside some given group, then the separability is really saying that the subgroup that you're considering is closed under the profinite topology. But usually that's not the at least usually for three manifold topologists, that would not be the way that you directly think about this problem. So if you want to think about a concrete model for this problem, what you're considering is really that, let's say you have any three manifold group, usually hyperbolic or non-geometric three manifold group. Right, it's realized by some three manifold M. And then in your setting, you're starting with some surface subgroup that is really represented by some immersed surface. Because of a dimension, you can always make it immersed. And to make it a subgroup, you want it to be pi1 injective. Okay, and the question is really that by trying to show S is separable, you're really trying to find some finite cover M tilde, so that you can actually find some lift of your immersion into this finite cover, and now you want it to be an embedding instead of just an immersion. And of course, we are talking about group theoretic objects, so you want to allow this diagram to commute just up to homotopy. That's so the question here is really that given some immersion like this, okay, whether or not you can find a collection of these objects with the properties that is described in this diagram. Okay, so if this holds, then you can say that the subsurface S you can say that the subgroup S is actually separable by some theorem of Shetitsky and Weiss. Okay. Perhaps I should say a little bit about the motivation or background of this problem. This is really related to this virtual Haken conjecture at the very beginning, because suppose you have some non-Haken manifold M. In order to show that M has a finite cover to be Haken, that is equivalent to say, or you can break your task into two steps. The first step would be trying to construct some immersion into this manifold M to be pi1 injective. And the second step is that trying to lift this immersion to be an embedding upstairs. That will give you the Haken case. And actually, this was successfully done for hyperbolic manifolds. To construct this immersion, that's the work of Kahn and Markovich, the celebrated subsurface theorem. And then to show its virtually embedding, that's the proof of, my advisor Ian Nagel, and based on previous works on virtual specialness, Danny Weiss and various people did a lot of work in solving those big conjectures. Okay, so at least at this point, we can kind of say that the problem here is successfully solved, at least for surfaces inside the hyperbolic manifolds. Actually, you can say more. So let's start by trying to look at what really happens if M has no non-trivial decomposition. So if M is cipher-fibered or hyperbolic, then we can get a fairly clear picture of what happens. So you can concretely think about, suppose M is cipher-fibered. The example you should really keep in mind is essentially that M is just a product of hyperbolic type surface crossed with S1. That's really the essential type. And then for, let's say, some hyperbolic type surface crossed with S1, then inside this three manifolds, what could those pi1 injectly immersed three manifolds be? One of them is clear. You can look at an arc, properly immersed arc from one boundary to another boundary that lies inside F. Then over it, you actually see this annulus formed by the fibers. That will give you some so-called vertical annuli. So that's one type. Vertical subsurfaces those are always annuli. And if some surface is pi1 injectively immersed and it's not vertical, then necessarily you can homotop it to be a so-called horizontal position. Typically, that would look like, for example, some finite cover of F and just embed it as one of the factors. And there are some other kinds of horizontal surfaces. This is a fiber bundle with fiber type F, and then it can fiber over the circle in other ways, and that will give you some horizontal surface other than your F, and you can mix the constructions to get more complicated horizontal ones. And for hyperbolic, surface, we also have some dichotomy of subsurfaces based on the theory of subsurface in hyperbolic geometry. So instead of vertical and horizontal, you actually have surfaces to be classified either geometrically finite, or actually in 3 dimensions, that would just mean the surface is quasi-Fuchsian immersed subsurface. Or it is geometrically infinite. The word geometrically infinite sort of suggests that, okay, this is the really complicated one that is hard to understand. But fortunately, for 3 manifolds, this has a very nice characterization due to I think there are many people who contribute this theorem, so let me not specify who was the main contributor. Geometric infinite case, then this surface is virtual. It's a virtual fiber, which means if you look at this surface, then you can pass to some finite cover manifold M, and then that cover will just be a surface bound over a circle, and the fiber is exactly what you saw downstairs. Okay, and if you just keep these two examples in mind and compare with this dichotomy here, you can actually see that horizontally immersed subsurfaces in fiber space are also virtual fibers. And the vertical ones sort of have similar behavior in the sense of certain quasi-convexity, but let's not specify what really happens to those because they're easy to understand. And if you look at what we have listed here, you can summarize and say, okay, if M is cipher-fibered or hyperbolic, then all the pi1 injectively immersed subsurfaces are actually virtually embedded. That means for geometric M, then you can always solve this problem. So immersed subsurfaces are virtually embedded. Okay, so really the if you so I mean the next step would naturally be wondering, okay, if I consider those surface subgroups, is it always separable inside 3 manifold? Then the story becomes slightly more interesting if you think about non-geometric manifolds. Actually, for graph manifolds, there are some examples given by Rubinstein and Wan saying that there are non-separable surface subgroups. So let's consider. So just based on our knowledge about the geometric case, then what we have here is that we have a 3 manifold, and I can break it in non-trivially into geometric pieces. And what I know is that if I simply look at the restriction of the surface inside each piece, then I already know that I can pass to a finite cover of that piece so that the surface is embedded upstairs. And so if we look at the non-geometric case, the real question is about if I can, since I can lift the surface piecewise to be embedded, whether or not I can match them successfully along the JSJ tori so that in the end I actually still get an embedded surface. So what could go wrong is, like, locally there would be no self-intersection, but you might have a lift so that if you go through some loop, then somehow it comes into the same piece, but through some other branch so that it intersects itself in the beginning. Okay, so that's really some question about the decomposition. So maybe it's easier if we introduce some language to some terms to say that. What I have here is that I'll have a decomposition of manifold M drawing a cartoon, that would be okay. Maybe I can break my 3-manifold M along tori so that it's broken into geometric pieces. Maybe this one is, for example, hyperbolic, and this one is cipher-fibered. This one maybe also cipher-fibered. Then I can schematically draw this picture as the dual graph where I have a vertex for each piece, and I'll have an edge for each of the torus. So I see actually there are 2 tori, so that these 2 pieces are adjacent along this tori. So this is actually the picture, the dual decomposition graph for this picture. All right, then what happens if I have a surface S that is immersed into the 3-manifold M? If I try to just homotop this surface inside M so that it has a minimum number of components intersecting the embedded tori, then what I have would be there is some induced decomposition of S. Just to draw an example, some arbitrary example of the surface S, So let me use some if this is a yellow one and this is a green one, and maybe I have a red one. Then what I see inside S, if you look at the preimage of this tori, then that would be just a collection of curves that decomposes S into different components. It might not be one-to-one correspondence with number of pieces inside here. For example, this guy, let's say something like that. This guy might be somewhat funny, and there might be a single one that goes through this green one, and after doodling around and then just go back. Okay. So I might, if I have an immersion of S together with a geometric decomposition inside M, I have an induced decomposition of the surface S. Then you can also try to just draw this picture with vertices. So you will have an induced decomposition of S, and there is an induced map between these 2 graphs, decomposition graphs. Okay, and I guess I'll usually just denote the corresponding surfaces by S sub V, where V are just vertices of the dual graph, and maybe JV, meaning JSJ, for each of the vertices of M. Okay, so what we have said is that there are possibly 4 types of the vertex subsurfaces S sub V. That would be, okay, depending on which kind of piece it lies in, and depend on whether or not it's a virtual fiber. It will be, okay, vertical or horizontal. and it could be quasi-friction or virtual fiber. Okay, I'm putting this in this form because I try to emphasize the similarity between corresponding terms. In particular, I can actually try to construct a subsurface of S consisting of only of these two types of subsurfaces. So piecewise, they are just virtual fibers, and if I try to glue them together along their boundary, then I would imagine that the surface would correspond to some virtual fiber. But there are some cases that it cannot really be embedded. So I'll just call this union of such surfaces to be the almost fiber part. That is induced by this decomposition and the immersion, and denoted to be phi sub S inside S. Okay, so what's good about this almost fiber part? In the rest of the talk, I guess what I want to try to convince you is that the question about this virtual embedding property can be actually answered by purely looking at the restriction of the immersion at the in the almost fiber part. So let me put the simple version of the theorem here. That's given the setting above, then S is virtually embedded. Turns out the other types of subsurfaces, there would be no issue about this gluing or the problem that I described before. And the embeddedness is really a property regarding the almost fiber parts. Furthermore, in fact, you can actually find some nice invariant associated to this almost fiber part that is completely computable, and I mean, the geometric meaning of that quantity would be kind of clear, I hope, after I explain to you. So. I mean, if you just look at the statement above, it's barely useful because how would I know that phi of S is virtually? David?
Maybe you were planning to get this later, but can you explain how this interacts with the work of Shititsky and Wise on the kind of virtual specialness of the mixed manifolds?
Oh, yeah. Thank you for bringing up this point. So as I said, the virtual embeddedness is only a problem about the almost fiber part. That means I can successfully take care of the other parts. In particular, if you want to show that the quasi, so first of all, if you want to show that the quasi-friction immersed subsurfaces to be virtually embedded, that definitely uses some results that are used in virtual Hawk conjecture proof. And you are also considering those geometrically finite subsurfaces gluing together along those tori. And in order to solve the issue of virtual embedding, for that part, I think, first of all, the ingredients are one of the important ingredients is the work of Shititsky and let's say include Shititsky. And Weiss, that's one of the things. And the other thing is that what I described above is only saying that S can be virtually embedded, and in order to see that corresponding subgroup is separable, that is also a theorem of Shititsky and Weiss. They actually have shown that embedded, pi1 injectively embedded subsurfaces are separable. Okay, so so both technically and conceptually, I need to use their results. Hope that answers your question. Okay. All right. So let's come back to look at try to focus on the almost fiber parts, and at least conceptually we can, in order to solve the question above, we can ask the following questions. So the first question is, if you look at the almost fiber part, what is really this obstruction? What is that? And the second thing is, if I know the obstruction, do I have an effective way to compute this obstruction? And I guess the third thing is, okay, I do know some obstruction to detect non-separability, but do I have any ways to construct an example of non-virtually embedded subsurface? Okay, turns out in some cases you can actually construct these virtually embedded subsurfaces, and I guess if this is if M is a graph manifold, there are previously known methods to construct such examples, and I guess one of the questions is that if you only have hyperbolic pieces, but it's a non-geometric manifold, whether or not you can construct a subsurface. I guess I can say up to now is that well, in certain cases you can construct those manifolds with only hyperbolic pieces and having non-separable subsurfaces. So a quick example of the manifolds would be some mapping torus of a surface map. So what I want to do is that, okay, I'll first take a torus. I try to briefly explain the example and try to claim that there is something interesting inside. Okay, so I'll just take a pseudo-anosov map phi onto this surface itself. Now it has a boundary component. What I can do is that I can look at negative of this surface and look at the mirror of phi phi. So I'm really trying to first look at the double, and then I want to do some surgery along this. Okay, I guess. I can take negative phi acting on the mirror of the surface, and then these two together will just give me some surface automorphism of this surface of genus 2, and it does has a reduction locus which is fixed. And furthermore, I want to take a dentist, let's say d of c. Okay, so at the end, I want a surface automorphism that is the double of phi composed with a single dentist along the locus. This is just notice that this locus is totally fixed by this double, so these two components actually commute with each other. There's no ambiguity in the definition. Let's denote this as C. Then the claim of the example would just be that the mapping torus of C just contains a non-virtually embedded subsurface. Yeah, so to get the complete construction, I guess if we have time at the end of the talk, I guess we can go into some details. But at this point, let's look at some easier problem just inside the graph manifolds. I'll tell you usually how people construct those non-separable surface subgroups. Then once you understand the analog between the cipher surface case and the hyperbolic case, you can try to carry that part onto this. Okay, so so let me try to first tell you what kind of obstructions that we're looking at. We should look at, and then for graph manifold, you have a fairly direct definition for that obstruction class, and then we'll try to explain how to generalize it to hyperbolic case. So I guess I should say that what I'm explaining now is actually the construction of Rubinstein 1 in back to the 90s. And the so-called Aspirality is actually their invariant if you just look at graph manifolds. So let's consider their construction first. Actually, what they have done is essentially that the case when your manifold M is a non-trivial graph manifold, which means there's actually no hyperbolic piece. And they are considering actually so-called horizontally immersed subsurfaces in graph manifolds. That would simply say that immersed S. That's just saying that the almost fiber part is exactly the manifold itself in our terminology. Okay, so as the picture does, let's come back to the problem before. Your basic question is that, okay, suppose I have a horizontally immersed surface S, and suppose it is virtually embedded. Then you can definitely say that if that's embedded upstairs, that would definitely be a fiber of the finite cover. Okay. Then in that case, supposedly it should be easy to understand the covering of M corresponds to the surface subgroup S. So instead of looking at the manifold M here, we can look at the cover of the manifold M and this cover just corresponds to the image of pi 1 S inside pi 1 of M. So this is, if you think about this, this is actually homeomorphic to the surface crossed with R, and in each piece it is exactly the vertices subsurface crossed with R, but it is usually glued up in an interesting way. So schematically, if you want to try to draw this space, because at each surface S sub V, you just have a horizontally embedded subsurface inside the cover. So what you see is that each corresponding vertex of the decomposition just give you a surface of the form. Just draw some random picture of SV, and the corresponding pre-image of the JSJ piece would just be homeomorphic to SV crossed with R, something like this here. And you're in the graph manifold case. So in the cipher fibered piece, each of these pieces is actually foliated by these cipher fibration lines, which are just real lines. And you do have a action of S1, which give you action of the real axis. So you do have a flow on each of these pieces. And except that you're gluing them, you're not matching those flow structure. So you only know that you have a surface at maybe time 0, and if you just flow along the in the time units in each piece, then after the time 0 start to mismatch with each other. So let's don't worry about that. Okay, but what's our task? We're trying to find a finite cover of M so that S is an embedding. But if you think about this picture, you're basically saying that, okay, I can look at the deck transformation of this surface inside this piece. I might have a number of different deck transformations. And okay, so the strategy is basically that you can look at one of the surface, and then you can look at, there should be another deck transformation image of the other vertex group nearby, then I can try. Okay, some of them may be not homeomorphic to this guy, but the surface is actually a virtually normal subgroup. So you can pass to some, you can always find someone, and the nearby piece would be definitely homeomorphic to the zero slice. Okay. If your picture is complicated enough, what might happen is that I'm trying to attach another homeomorphic piece just when I cross, each time when I cross a cylinder that covers a JSJ torus. If I can successfully do this extension, and finally maybe after several steps when I come back, there are two possibilities. One is that I might see that when I come back to this piece, I'll have a surface that exactly matches up with the starting surface inside that piece, inside the initial piece. Or it could be possible that this guy comes back, but it does not match up with the initial one. So essentially what I have here is that if I have this surface S, and suppose I can find some other place that I can do this extension of elevations so that I can get a compact copy of the surface S homeomorphic, then in that case, I can look at the chunk between zero slice and maybe this T slice, and I can project it down to M to get a finite cover. Otherwise, what happens is that I try to do the extension upstairs, but at sometimes when I come back, I get to some other level. So what I end up getting is that if I continue to do, I will get a spiral surface that starting from here, maybe when I come back, I'll go to some higher level, and then some further higher level. In that case, I will not get a compact surface. So you can sort of see that the height of those levels, if you try to measure it in the parameter t, that will give you some invariant, maybe the height of the corresponding levels. That can tell you whether or not you can find this manifold M. So that's, I guess, that's the general idea, and let's try to translate what we have observed into something, into some data purely depending on the manifold M downstairs. Okay, so to recapture, what we have here is that, maybe I have some different circles that are mapped to different tori inside the three manifolds. So, okay, what I want to construct, is given this immersion, I want to construct an invariant that is, whenever I have a cycle inside the almost fiber part, in this case, that would be the surface itself, then basically I want to associate to any cycle a non-zero rational number. And I want to say that, okay, my surface is separable if and only if this invariant takes only values plus or minus 1. If that's not plus or minus 1, that would basically mean that in that picture you might come back along some cycle and go into some other level, which is different from itself before. Sorry? Yes, it's actually only an invariant about the dual graph. Yeah, but let's just write it as the almost fiber part and does not introduce any more information.
Is it possible right there, in that horizontal surface, it was nice and compact, restricted to like each of the sections, but in another lift within that section, it could spiral around?
Yes, that could be possible. I'm saying that your, virtual fibers are essentially you need to pass to some finite cover so that the surface subgroup is normal in that subgroup. So that's of course possible that there are some other, for example, some other deck transformation of this point, but it just sits in some spiral surface purely inside the given surface. So that's why you usually need to pass to some integral multiple in order to find the surface to start with. Okay, turns out it's quite easy to describe this invariant in terms of topological data when you have an alpha that is a cycle of Vs, then alpha would just look like something inside here, and it intersects a number of decomposition curves. Like in this picture, it intersects 2 of them. Okay, so let's say C1 to Cn inside phi of S that are just decomposing curves coming from the JSJ decomposition. Okay, so what's the image of this surface, this curve C inside the inside 3 manifold that just sits on some torus, some JSJ torus? But you're with graph manifolds, so you actually know that there are regular fibers that are given by the cipher fiber pieces. And each JSJ torus is adjacent to 2 cipher fiber pieces. So you actually get 2 different regular fibers coming from different pieces. And by taking the intersection number, you can there are actually 2 ways you can get an intersection number, and we'll take a ratio of it. So Ci lies in Ti, and the Ti receives 2 different regular fibers on adjacent pieces. Let's denote as Li plus or minus. Then your invariant S is basically defined to be just a product of the intersection number. Let me use another color I to distinguish. Ci Li plus over intersection of Ci L I minus, and the ratio is taken with the product 1, 2, n.
Is the point that you know which one is plus and which one is minus along an orientation of alpha?
Yeah, you're going along alpha, and at first you meet the L minus, and then you meet L plus. Okay, and of course in this expression you always get a positive rational number. It's just counting geometric intersection. And I'm writing this, I'm allowing negative values because you actually can introduce a generalization for non-oriented surfaces immersed in 3 manifolds. Okay, so I guess this is really the theorem of Rubinstein 1. That in the setting above, then S is virtually embedded if and only if the little s takes value S is constantly 1. So there is no non-trivial ratio. If you know that, then you know the surface S is virtually embedded. That's our idea. And our task is basically trying to generalize their picture to the cases where hyperbolic pieces are involved. So let's just try to look at their formulation and see what are the corresponding objects, or what are the things that are now not quite available. In cipher fiber pieces, I do have these regular fibers in each piece, and that's something not available for hyperbolic pieces. You don't have a central element that give you a given direction. But there are some substitute for that. At least, let's say for mixed manifolds, which means hyperbolic pieces might be involved, there is a nice way to get such a structure. Remember I said that you're looking at the ciphered action of S1 that will give you some flow. But you know, if you have a fiber bundle, you will get some suspension flow associated to that. That would be something helpful. So at least if we try to directly mimic what they have done, then we want to generalize it to the special case where I have an automorphism of a surface, then I can try to make use of the suspension flow. The good thing about mapping tori of surfaces is that there is this Nielsen-Thurston classification that tells you every automorphism basically breaks into different pieces. After taking some power, you can get a decomposition of phi into different pieces. On some pieces, you get pseudo-anorthof. On some pieces, you just get trivial action, etc. And because you have this, the singularity or the prong structures on each of the boundary components, the suspension of that action will basically give you a unique slope that can take place the role of the Li there. That's called the slope of degeneracy. So in this picture, can use slopes of degeneracy instead of Li plus or minus. I guess technically you want phi to fix all the periodic points that appears on each of the reduction curve. But that's not completely the same as the setting here, because if you try to spell up this proof, you will notice that the horizontal condition actually tells you the surface is transverse to the flow. So you also want to keep that assumption here. And S is transverse to the suspension flow. It's quite like the example that I'm describing there. In this case, you can directly use the slopes of degeneracy instead of the regular cipher fibers, and the formula also holds for that case. And then you try to look at the proof that you have come up with. You will notice that this formula here, by looking at the intersection number between different geometric objects, that's not really necessary. What you really need is the way that any horizontal SV becomes virtually fibered in its vertical piece, in its vertex piece. So you can actually translate this formula of intersection numbers into some formula with covering degrees involved. In that way, you can actually get some formula not so much like the invariant before, but still for M, it's defined by a different formula, but you still have S from the almost fiber parts to rational numbers. And there is a similar theorem like the Rubinstein-Wang theorem that virtually S is virtually embedded if and only if the image takes only values plus or minus 1. Okay, so I guess I don't really have time to explain the actual surface that you want to construct inside this suspension, but at least let me try to draw a picture to give you some hints of what happens there. So you look at this suspension of surface, and it actually has two different hyperbolic pieces. Just draw the surface, and you think of to be a suspension. Okay, so what I do is that I'll first look at a covering of each piece, and then I'll try to match them. In some way like this. This is not a closed three manifold, but it's called a semi-cover in the sense that away from the boundary, that's just a cover. And on here, it just matches up when it grow. Glue them on the downstairs. Okay, the reason that you want to pass to a semi-cover is basically you can construct the embedded object inside here, and after projecting, you can try to glue them downstairs to get immersed ones. after, you can don't worry about these two pieces. Then what you can do is that you can try to find the two slopes that have image match up with each other, and you can also have, and you can make sure that this slope is different from that slope, so that will give you some difference inside the formula here. And then these are some slopes that are randomly choosing. At this point, there are some fairly well-developed methods, I guess, by Shititsky and Weiss, and in their paper of about mixed subsurfaces. Then you can actually close this open ends by some other surfaces that are quasi-functions, so that won't affect that part. Okay, so eventually what you see is that if you project this surface down and try to match these two up, you get some obstruction by looking at a slope like that, a cycle like that. Okay, so I hope that sketches pretty much the idea of the work, and I want to stop.